Have you ever just stopped and looked at the world around you? I mean, a solid table, a glass of water, the air you're breathing right now, and just wondered, what is all this stuff really made of, deep down? It's a massive question, one that people have been asking for thousands of years. And today, we're going to try and answer it.
So you see this iceberg, right? It looks like one big, solid thing. But believe it or not, it has something fundamental in common with the very water it's floating in and the air all around it. And what they have in common is this really old idea that everything, and I mean everything, is actually made of tiny little individual pieces. But this whole idea that everything's made of particles, it wasn't always the accepted truth, not by a long shot. In fact, for centuries, it was at the center of this huge debate, a real battle for the heart of matter itself. So on one side, you had this guy, Democritus. He basically said, look, if you keep cutting something in half over and over again, eventually you're going to get to a piece so tiny you can't cut it anymore. He called it an atom. But then on the other side, you had Aristotle, a superstar of his time, and he argued that nope, matter is continuous. It's a seamless whole. And for a very long time, Aristotle's idea won. It took modern science, with actual experiments, to finally prove that Democritus was on the right track all along.
Okay, so if everything's made of these tiny particles, how can we get solids and liquids and gases? What's the deal? Well, it all comes down to how those particles are arranged. So let's start with solids. Think of the particles in a solid like a perfectly organized crowd of people packed in shoulder to shoulder. In a solid, the particles are locked into this really neat, orderly pattern. The bonds holding them together are incredibly strong. They can't just wander off, but they're not totally still either. They're always vibrating, just a little bit, right in their spot. And as you can see, there's hardly any empty space between them. But wait a second, how do we know there are spaces in something that looks totally solid? Well, check out this simple experiment. If you touch a piece of chalk to a drop of ink, you can actually see the color climb up into the chalk. Now, how could that happen? The only way is if the ink particles are finding and squeezing through tiny, invisible gaps between the chalk particles. Pretty cool, right? And that's it. That's the whole secret. That super-packed, rigid, orderly structure is exactly why a solid has a definite shape. The particles are locked in place, so the whole thing just holds its form. It's why a rock is always a rock. Okay, so that's solids, but what happens when we loosen those bonds a little bit? Well, then you get liquids. If a solid is that tightly packed crowd, a liquid is more like people mingling at a party. They're still close, but they've got some room to move around. Now, in a liquid, the particles are still buddies, they're still close, but that super rigid structure, it's gone. The bonds between them are weaker, and that means they can slip and slide right past each other. They have a kind of freedom that particles in a solid just dream of. And you can literally watch this happen. Just look what happens when a little crystal of potassium permanganate gets dropped into water. The purple particles don't just sit at the bottom. Oh no. They start to spread out, they move, they dance their way into all the empty spaces between the water particles until the whole thing is just purple. And that's the key right there. That ability to slide around is precisely why a liquid doesn't have a shape of its own. It just flows and takes on the shape of whatever is holding it. A glass, a bottle, a puddle on the floor. All right, we've done solids, we've done liquids. Now it's time to crank things up to 11. Let's talk about gases. If a solid is an orderly crowd and a liquid is a mingling party, then a gas is a full-on mosh pit where every particle is just going wild. With gases, all bets are off. The bonds between particles are basically non-existent. They are super far apart from each other. There's tons of empty space, and they're just zipping around freely and randomly in every possible direction. Total chaos. And check this out, because this is wild. At the bottom, we've got a jar of this brown nitrogen dioxide gas. It's heavier than air. On top, we've got a jar of just plain old clear air. So what happens when we pull out that divider? Does the heavy brown gas just stay put at the bottom? Absolutely not. It spreads upwards, completely defying gravity, to mix with the air and fill up both jars. And that incredible random motion is exactly why gases don't have a fixed volume. Because their particles are moving so freely, they will always expand to fill every single nook and cranny of whatever container you put them in. Now, this difference in spacing also explains something you've probably experienced yourself. Squeezing a syringe full of air, it's easy, right? You're just closing up all those huge empty gaps between the particles. But try doing that with a syringe full of water. Good luck.
It's almost impossible because the particles are already packed so tightly together, there's just nowhere else for them to go.
Okay, so we get it. The arrangement of particles gives us solids, liquids, and gases. But what are the particles themselves? What are the actual fundamental building blocks of our world? Let's zoom in even further.
At the most basic level, you've got what we call elements. You can think of them like the Lego bricks of the universe. They're the pure, fundamental substances. You just can't break them down into anything simpler, at least not with chemistry. Like copper here. Every single particle in this chunk of metal is a copper particle. It's just copper, pure and simple.
Or take a look at sulfur. It's a completely different element, a different building block, with its own unique properties and that unmistakable bright yellow color.
And then you get something really cool, like mercury, which is famous for being one of the only elements that's a liquid when it's just sitting on the table. But it's still a pure element, made of nothing but mercury particles.
But here's where the real magic happens, when these elements start teaming up. They can combine chemically to form compounds. Take water, for example. It's made from two elements that are normally gases, hydrogen and oxygen. But when they bond together chemically, they create a totally new substance, a liquid, with completely different properties. It's incredible. So let me ask you, how many of these basic building blocks, these elements, do you think there are to make, well, everything? Thousands? A million? The answer is kind of mind-blowing. Right now, we only know of about 120. That's it. Think about that for a second. Every single thing you have ever seen or touched, every rock, every plant, every star, even you, is made from some combination of just those 120 or so elements. It's like the universe has this tiny little toolkit, and with it, it's built millions and millions of different things.